Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let's illustrate the limit, law, or theorem for any linear function. A linear function is a function with the highest degree of the variable being 1. One example is this. Let's have f of x is equal to, let's say, x plus 3. Okay, this is a linear function because the exponent of x is just equal to 1. The limit theorem for this is simply using the idea of substitution. Now, there are some cases later on that might be different. So we're going to have a separate video right after this to discuss a certain concern before we proceed to the other few theorems that will use the idea of substitution. That's the usual thing we do in solving for limit. We use substitution. But before we proceed to the next few theorems right after this, there's a separate video that will also help us understand some concerns that are not true to all. Well, anyway, the limit theorem for this is simply this one here. The limit of a function as x approaches to a certain c. Here, of course, our function, generally, the linear function is written as ax plus b. Don't forget that we have here parentheses because we're talking about one singular function. As x approaches c, the idea here is simply substitute c to x. You have ac plus b. You operate those numbers and you will get your limit. That's the limit theorem for a linear function. Simply substitute your value for c to your x and operate and you will get your limit. Now, before we talk about this, if you were able to forget the idea of substitution or this, you can always go back to the first two limit theorems. The limit theorem of the constant and identity. Because if we talk about this one here, just a little inserting idea. As x approaches, let's say 3, just say it's a 3, right? So we have here the limit of our function, again parentheses. Now I already discussed the idea of involving parentheses because there are some cases that if you will not include parentheses, then you're just trying to get the limit of the first term. But of course, it's just the result is just the same for a linear function, but let's just practice it all throughout. As x approaches to 3, you can break this into two forms. You have the limit of x as x approaches to 3, and you add here the limit as you distribute the notation for the limit of 3 as x approaches to 3. Okay, now in this case, you have a limit of an identity and a limit of a constant. The limit of identity, as discussed in limit theorem number 2, is the value of the variable that is approaching to. So you have 3 here. And the limit of the constant, okay, limit of a constant, let's try to have a different value so that we could really separate the idea here. Okay, let me use here x plus, let's say, 2. So you have here x plus 2 and limit of 2. Okay, so we have the limit of a constant is the constant itself, so plus 2. So the limit of this function using the first two limit theorems is just 3 plus 2 equal to 5. Okay, this is by using the first two limit theorems. Now, what if we're going to use this limit theorem, the limit theorem for a linear function, where we simply substitute immediately? You will have here, this is the limit of our function as x approaches to the same value earlier so that we can differentiate them. This is the limit of x plus 2 as x approaches to 3. So simply substituting that, you will have here 3 plus 2 equal to 5. So we have the same result as applying the first two limit theorems and this limit theorem right now. Of course, our limit theorem is in general form where we have here a certain a. Our a in this given function is just equal to 1, the coefficient of x. But if we have another function, g of x, let's say 3x minus 7, applying this limit theorem by simply substituting the value of x, you will have here the limit of, let's say, g of x as x approaches to, let's say, negative 1. Let's say negative 1. So you will have here the limit of the entire function 3x minus 7 as x approaches to negative 1. Okay, so simply substituting that, you will have 3 times negative 1 minus 7. You will get a result That's negative 3 minus 7, negative 10. So you don't need anymore the idea of the the identity function, limit of identity function, limit of the constant function. Simply need to use this limit theorem. This is example 1, by the way. This is example number 2. Okay, let's have last one example here. Let's have h of x, where it is actually 6 minus 2x. Okay, and then we're solving for the limit of h of x as x approaches, let's say, negative 1/2. Okay, negative 1/2. So we could try fractions. So we will have here the limit of 6, again parenthesis, minus 2x as x approaches negative 1/2. So simply substitute that on our given. So you have 6 minus 2 times negative 1/2. That's 1. Double negative property. So 6 plus 1, you will get a result of 7. This is the limit of the third function. So the limit theorem for a linear function allows us now to substitute. But our next video, before we proceed to limit theorem number 4 and so on and so forth, there is a concern and a good discussion as to why is substitution a technique but not all correct in all forms of function. Okay? I mean, there are some functions that the resulting may not be true, or they are not the same. Okay, so we are going to find out the result on that video before we proceed to the limit theorem number 4 and so on and so forth. So what are you waiting for? Subscribe now.